Hello AP Physics students. In this video we're going to be talking a little bit about the concepts in Chapter 3, which we're going to be covering some advanced nonlinear motion. Of course we'll be talking about this a little bit in class as well, but these are some of the basic things that you can go back and look at again and again. In this chapter there's quite a few things that we're looking to do. We want to make sure that you can represent position in both 2 and 3 dimensions. So this is a little fancier than what we did with one-dimensional stuff. And we want to be able to determine the velocity of a particle, knowing what its path it's taking. So we want to be able to look at instantaneous velocity in different places. We want to be able to find the vector acceleration of a particle, interpret what components of acceleration exist, including with circular motion, and we want to be able to describe projectiles with a curved path of a projectile based on position, time, velocity, acceleration, a lot of things. I want to cover some key ideas behind circular motion and also talk a little bit about relative velocity. What's nice about this particular unit is this chapter in this unit is that a lot of this stuff actually, there's not much new to tell you here. It's more a refresher of some things. So I'm not going to spend as much time in Chapter 3 as I did in Chapter 2. But I do want to talk about some things. So the first thing I want to talk about is some notation. In fact, most of the advanced things that we need to discuss in this video, in this chapter, really describe notation issues more than anything else. This is the real advanced stuff here. What I want you to do is really consider what vector addition looks like, and just keep in mind what vector addition you kind of did the first time you took physics. Pretty much, these were the questions where you had something like, hey, a camper, hikes 50 meters at 30 degrees north of east on one day. 50 meters wouldn't be very much. 5 kilometers. And then the next day, after they make camp, they get up and they go another 3 kilometers on day 2, but they go 60 degrees northwest. And so when you're asked to add those vectors together, pretty much what you're doing is you're going to break that vector into its components. You're going to say, all right, how much of that 30 degrees, the 5 kilometers at 30 degrees, how much of it was actually east and how much of it was north? So this was called vector resolution, when you took the hypotenuse of a bow tie triangle and you broke it into its components to find the sides of the triangle. Vector addition was the opposite. If you knew the components, the sides of the triangle, you could use Pythag to go ahead and find the hypotenuse of the triangle. That should be vaguely familiar to you from the first time you took physics. Well, here, as you can see in figure 3.1 from your book, we're basically doing the same thing, but we're using this position vector notation to say, yeah, the resultant displacement of the particle r, starting at the origin and ending at point P, that is made up of, it's three-dimensional. It's made up of a component that was horizontal, and so that's the x component, a component that was vertical, so that was the y component, and another component that moved along the z-axis into the border, out of the border. And so we see that if you take the horizontal component and you take into account the vertical component, and then you take into account this forward and backward component, that in three-dimensional space, it takes you to a new position in space. The best way to think about this, and we're going to do an activity with this coming up here, is with rocket golf. I'm going to have you do an activity where you're going to fire Nerf rockets from cones to cones like you would on a golf course. You have to get from one cone to the next. And I want you to really consider that some of these cones are on the first floor, some of these cones are on the second floor, some of them are up high above doors on window ledges, and some of them are down low on the ground. If you had to go through and add all the components of three-dimensional motion, what would a three-dimensional map of the position of those cones be? Could you describe it in terms of left, right, up, down, forward, and back? So when we do that activity, that'll really help you, I think, picture this a little bit. But essentially, what we're interested in doing is adding up all the x components, adding up all the y components, adding up all the z components, and that gives you a new position vector. After you understand position vectors, then we start to look at a new notation for something like average and instantaneous velocity when we're talking about something that might be a two-dimensional vector. That is, it's not motion along a single number line along one axis. You're not just moving left and right or up or down or forward and back. If it's a two-dimensional vector, which means it has a component that is left and right and maybe up and down, or maybe it has a component that's up and down and forward and back, but it's got more than one axis involved. Now, when we think about finding that average velocity, you can see that the notation that I've included here from your book, we're looking at average velocity just the same way we always have. It's always displacement over time. But now we're viewing that displacement as a resultant vector instead of a displacement. It's the resultant of more than one vector. So it might be the resultant of, say, vector number 1 and vector number 2 combining to make this resultant vector. And therefore, the average velocity which you move through that is going to be the change in that component, that position component, the resultant position component over time. So the particle's path itself might be a curved path, something that's not linear at all. But if you want an instantaneous average velocity, what you're really interested in is just those 2 points in time. So when we look at instantaneous versus average, all we're looking at here is writing the same thing we did back in the first chapter in the unit in a slightly different way, looking at it from the point of view of a unit vector and taking the derivative of position and time to find instantaneous velocity, or finding the slope of a line between 2 points on a curve to find average velocity. This is the same concept you used back in the first chapter of the unit, but you're just looking at it in a slightly different way. The notation looks a little bit different. What's really important to understanding the stuff that's two-dimensional is that we do like to break our vectors into components. And here's a classic example of a particle that's moving along a curved path. You can see that curved path indicated here in the figure. And at any particular moment in time, we might be interested in what the instantaneous velocity of that particle is. And the instantaneous velocity will have a magnitude and a direction. Okay, so this is your magnitude, the length of that vector, and the direction is the angle. And that's just what it was at that moment in time. And then what we like to do is we like to break that into components. We like to say how much of that was horizontal and how much of it was vertical. Of course, you can transpose this over if you want, but this is pretty common among projectiles. It's not that unusual for us to look at projectile motion back when you took physics the first time and say, hey, break this initial velocity into its x component and its y component. Well, now we're doing the same thing, but with a little bit of advanced knowledge, we can say, well, you know, how can we do that with derivatives? Well, you know, the velocity in the x direction is going to be the derivative of instantaneous position and time, but in the x direction. And same thing for y and same thing for z. This is just showing you that instantaneous velocity, the same things that you were doing with derivatives in chapter 2 still apply in chapter 3. So these derivatives, all right, these derivatives right here, they are exactly the same thing you were doing in chapter 2, but now we're just treating it from a component point of view. By the way, you wouldn't have to do it as a derivative. The same things can be expressed as unit vectors, where the unit vectors tell us that if you took the derivative and use I for x and j for y and k for z, that if you want to add up all these derivatives, you still end up with the same thing. You end up with the resultant velocity. Mostly what we're looking at here is notation, and confused about this or I'm being not quite clear, feel free to ask me, but I think the general idea is these are the same ideas that you saw when you took physics the first time. The only thing is we're just giving you some different notation. So let's take a look at a good example that I really like here in section 1. What is the use for this? How does this look a little bit different than what we did in physics? Well, I like this example about a Mars rover. I think it's particularly relevant now that we've got the Mars lander up there moving around. So this says a robotic vehicle, or rover, is exploring the surface of Mars, and the landing craft is the origin of the coordinates. And the surrounding Martian landscape lies in the XY plane. So, just kind of picture in your mind this rover moving along, and it's moving along with the following functions. They give you an X function that describes how it's moving left and right. Imagine you were taking a bird's eye view of it. You were watching it from above. All right. So how much it's moving left and right is described by this function right here, and how much is moving up and down. All right, not off the surface. It's not like levitating over the surface, but as you watch it from above, it's moving up and down. It's described by this. What they want you to do then is go ahead and find the rover's coordinates at its distance from the lander after 2 seconds. So you're just plugging in times. You're going to plug times into both of these equations, these functions. And those times are going to kick out positions. Now, that's great. You can find what its instantaneous positions are. And once you know its instantaneous positions, you can find the displacements. The answer to this, I've gone ahead and posted in graphical form here. And you can see that what's really useful to see here is that once you actually solve it out, we can see that the rover is turning. The rover is kind of turning to the left as it moves upward from this point of view. So the different displacements are easy. At time 0, all right, remember what you're looking at here are on these axes are both X and Y position. So time has got to be indicated in a different way. These aren't XT graphs or YT graphs. This is a Y versus X graph. So we can see by plugging in different times that when it's located at time t equals 0, it's located kind of here. And we can see that it's 2 meters to the right of the landing craft, all right, which is our origin. And it's moving with an initial velocity upward, or along the y-axis. So its displacement at time t equals 0 is just going to be easily calculated from plugging in times 0 into those functions. When you type in 1, you get a different xy position. You get a different xy position. And when you type in 2, you get an even different position. So we can see changes in velocity here. It appears to be speeding up. And it's accelerating because it's changing direction. So what we're doing was plugging in numbers here and then taking derivatives. This is kind of a classic example of what you would be using this kind of stuff for. So, what if you wanted to find the velocity? Well, the velocity is the derivative. So imagine you wanted to find the velocity in the x direction at a specific time. Well, what you've got is negative 0.25 t squared plus 2. So the derivative, that's x. That's its position, all right, at a specific time. So here, let me just get rid of that. That's the xt function. The velocity is going to be the derivative of that function, right? So it's going to be negative 0.5 t. So now plug in your time, and you've got it. So at 1 second, it should be its x component should be 0.5. All right. So as you go through and figure this out, this is what I mean by using the derivatives to find the velocity and plugging in times. You should be able to easily take a moving object function and kind of describe it in 2 dimensions instead of 1.